I'm glad this sort of question showed up. So the question is, which organic compound requires the least oxygen for the complete combustion of 1 mole of the compound? So you have, I think this is propanol, propanoic acid, no, butanoic acid. What do we have here? Propane, butane. Right? So I'm gonna guess it's gonna be either this one or this one, right? Like the lesser, how you say, the lesser carbons. And I'm also gonna guess it's gonna be an alcohol because I remember because of the extra oxygen, when you try to balance it out, you end up using less oxygen. But let's figure it out, right? So between it's either A or C because it just has lesser stuff, right? Lesser carbon. Let's see if we can, let's balance them all and let's figure it out. So you have A with C3H7OH reacting with some bit of oxygen to form carbon dioxide and underwater. And you have 3 carbons, this will never change, and you have, well, 8 hydrogens. You'll need a 4 here, so a total of, what is this, 6 oxygens and 4 oxygens here, a total of 10. But you have 1 oxygen here, so you need 9, so it's going to be 4.5, right? So that's the first equation. Let's erase all of this so we can work with B. That's not the best yellow in the world. You have C3H7COOH plus some oxygen and CO2, sorry. I think after this we don't need to do D because we'll have a good idea this won't be it. Okay, same principles apply. 4 over here, you have, again, 8 hydrogen. That's interesting. Yeah, we do. 8 hydrogen again, so that's a 4, right? And this time you have 4. That's 8 from here and 4 from here, right? What is that in total? 12. 12, from which 2 are already here. So you need 5 over here. That's the second question. Clearly more than our last one. Okay. C. That's still not our answer. I think A is our answer. Some oxygen and it'll produce carbon dioxide plus water. And you need 3 here and 4 here, 6. So exactly the same amount of oxygen is on the right hand side compared to A, right? 10. But there's no oxygen over here. So all of the oxygen should be here, so you need 5 oxygen for it to burn. So C requires more oxygen than A. So I'm pretty confident it is now A. The answer is A. Yes? Not that this question is difficult, but I think people forgot to consider all the electrons in the molecule. So one caveat, and I think most people ended up doing this question wrong. That's what the examiner report highlights as well, right? So the diagram shows the structure of hydrazine. This here is hydrazine, and we have got to figure out how many electrons in total are involved in bonding and total number of electrons not involved. So total, not just valence, but all the electrons. So I think the best thing we can do, see if we can draw hydrazine. Is a dot and cross including the inner electrons as hydrazine or just nitrogen. It's gonna look really bad. Or let's just draw nitrogen, right? That's 2 electrons in its inner, and then you have 5 electrons because it's in group 5. 1, 2, 3, 4, 5. Nitrogen, when it pairs with 3 electrons, and the other 2 electrons in its outer shell are not bonded, because by sharing 3 electrons it can have a outer octet fulfillment. Yeah, so we've seen nitrogen just do, right? Like there's a reason nitrogen makes a triple bond with itself, right? And ammonia is a really good example. It makes 3 bonds. Hydrazine is like, you gotta look at hydrazine. They show hydrazine a lot because they think that hydrazine is very familiar to ammonia actually, or like at least half of it, or at least this bonding is very similar to that of ammonia. So you see hydrazine a lot more, right? And I do make sure we do dot and crosses for hydrazine when we're studying bonding. So, and like people know this particular molecule by name. Otherwise, it's like you're not supposed to know it. Okay. So I'm gonna draw the dot and cross for hydrazine, but I think showing the inner electrons will get very difficult, so I'll just show the outer electrons. So that's 1 shared, 2 shared, 3 shared, and let's get hydrogen out. Hydrogen will be white. That's hydrogen. Okay. And hydrazine is also. Oh, it doesn't have 3 hydrogens. What am I doing? Let's get the other nitrogen here, right? Right? And both these pink nitrogens have 2 remaining electrons. Right? And each of them have 2 inner electrons which are on the inside, right? So total involved in bonding are all the outer electrons aside from these 2. These 2 are not involved in bonding, and these 2 aren't. So let's count the total electrons that are not involved in bonding. That's 2 from this nitrogen and 2 from this nitrogen, plus 2 of each nitrogen on the inside. So that's a total of 4 for each nitrogen. A total of 8 are not bonded. 8 are not bonded, right? And we can see all the bonded ones. That's 2, 4, 6, 8, 10. 10 ton are bonded. So what's our answer? C, D. D is our answer. Now, in a excuse me, a question like this, I just do not follow it unless I follow I make a diagram. So they're talking about sulfuric acid solution. So what ions are present? So the positive ions in the solution are, well, just hydrogen. It's just hydrogen because both water and sulfuric acid has the positive ion as hydrogen. And the negative ion, there are a couple. They're going to be the sulfate ion, and for water it's going to be OH. So there's no competition for the positive ion, right? What's gonna be liberated at the cathode right over, not over here, at the other side, right? What will be liberated? Well, hydrogen is gonna gain electrons and hydrogen ions will gain electrons and form hydrogen gas at the cathode. And between the two, OH ions will be liberated, right, at the anode, forming, well, OH ions will discharge, but the reaction ends up producing what? It's going to produce oxygen gas at the anode, right? So let's see what the question is trying to ask. Hydrogen is released at the negative electrode? Yes, that is true. We've already written that down. Oxygen is released at the positive electrode? That's also true, isn't it? Sulfur dioxide is released at the positive electrode? Well, yeah, no, right? Because it's not. The acid becomes more concentrated. Well, does it? Yeah. So the hydrogen is being decreased. So doesn't matter which hydrogen, from the acid or the what do you call it, from the water, but the OH ions are decreasing, so the more sulfate ions. So yeah, you can say the water is going away from here, so whatever is left is just the acid, and it's getting more and more concentrated. So that's also true. So the correct answer is 1, 2, and 4. So that's A. So that's A. Before we begin looking at the scary question, let's bring our attention to this abomination of a diagram. Now, one thing to note is that this is a battery, and at the negative terminal, there are like electrons are flowing into the system, right, or into the cell we have over here. So let's say we have like, never will that be the case, but let's say 10 electrons going in here, right? If there are 10 electrons going in here, what happens is that whatever reaction takes place over here, right, whatever reaction will take place, I'm sure it's going to be some sort of metal discharging, right, a positive metal absorbing electron and discharging, or even hydrogen, right? What happens is, on the other side, this solution also produces 10 electrons, right? Whatever's over here, the negative ion over here will produce the same amount of electrons, and so the total change in electrons remains the same. So think of the other way to think about it is, this is a closed system, nothing is going into it or coming out of it. So whatever electron transfer is come over here, if this part of the system is gaining, is committed in giving electrons, this part of the system is committed in taking electrons, and the net difference in electrons needs to be the same. And why do you think that? Think redox, right? Now these, like, we don't call them that, even in A-levels we rarely call them, but they also call them redox cells, because it's just exchange of electrons, right? With that in mind, let's kind of shift our focus to the bigger nightmare version of this. So let's do that same 10 electron thing. If 10 electrons pass through here, right, 10 electrons will be used to discharge whatever the positive ion is in this solution, right? But 10 electrons will also be produced over here, which will also go over here and do the same thing. 10 electrons will end up being, liberated from this solution and then go here. And the number will always be the same, because you're not creating or destroying electrons. So in every solution, 10 electrons are going, right? So that part is clear, right? Hope that makes sense. Yeah, so let's take a closer look. You have aluminum being discharged here, so aluminum 3+. So what does this 3 plus mean? Aluminum 3 plus requires 3 electrons. Aluminum 3 plus requires 3 electrons to turn to discharge, turn into aluminum. So if you had those 10 electrons, you'd have how many? You'd have how many aluminum being formed? Yeah, so in my calculator, I put 10 divided by 3 and I get 3.33. So I changed in my head, I changed 10 electrons to 10 moles of electrons. So my answer comes in moles because otherwise with 10 electrons, I'll only produce, 9. But with 10 moles of electrons, I'll produce 3.33 moles of aluminum. So let's write that down. I'm producing 3.33 moles of aluminum for that 10 moles of electrons passed. And 10 moles of electrons, you've probably never heard it, but 10 moles of electrons is just itne number of electrons. I could have used any number I wanted. I'm just using moles because my answer will be in moles and it's just easier to process from there. So with that same logic, how many moles of each metal, because 10 moles are going in all of them, how many moles of each metal will be produced? So let's figure it out. What's the equation for copper? Copper is, even the question says 2 plus will require 2 electrons to produce copper. So 10 will produce, I don't even have to put it, 5 moles of copper. This is producing 5 moles of copper. Lead has a 2 plus charge as well, right? So that's going to be 5 moles of lead, 5 moles of Pb2 plus turning into Pb. And the last one is silver. So silver has a plus charge, right? And this will require 10 moles, right? So far, so good. But the question is not over yet, believe it or not. The question is asking what is the increase in mass. So all of these metals, this is the amount of aluminum discharged. This is the amount of aluminum produced in moles. What is the mass of this aluminum? So can I change these moles into mass? So this is just going to be, I'm just going to multiply each of these mole values with their respective AR. So 3.33 times aluminum is 27. I'm getting 89.9 grams of aluminum will be produced. 5 times copper is 64. Wow, look at that. 320 grams of copper. Lead is heavy. 207 times, how do I know lead is heavy? Whoa, 1037 grams. So almost a kilogram. Way more than the aluminum and the so lead is so heavy compared to aluminum, even though you're producing like slightly double the amount. Like, take a look, you're producing double the amount, like 3.3, less than double. 6.6 would be, exactly double. But like, yes, producing, slightly more lead, but look at the mass difference. Like, this is about 100 grams, this is more than 1,000 grams, like more than 10 times increase, just because lead is heavier. Okay. And the last one, let's just put that, I'm not confident it's silver. 108 times 10, right, is, no, it is just by a millimeter, just barely, 1080 grams. So it is D, right? So you end up producing, let's start from here, you end up producing 89.9 grams of aluminum, 320 grams of copper, 1,037 grams of lead, and 1,080 grams of silver. Which solution would produce the greatest increase in mass in the cathode? Well, it's going to be silver. Yay! It's going to be D, which will produce the largest gain. So the interesting part is how I like these two are not even in the competition. But you had to kind of work this out. I don't see, because this question is so unique in its way, I don't think anyone had any back experience to kind of work this question out in how you say, like you had to solve it during the paper. You couldn't just go, oh, I'm very sure it's gonna be D or C, couldn't really do that. There's too many variables. You had to decide how many electrons, and then their respective ways are insanely different as well, right? I hope this explanation helps. Let's move on. The metals iron, lead, and zinc can be manufactured by the reduction of their oxides with coke. What is the correct order of ease of reduction of the metal oxides? So this is a brilliant, not really. It's just a okay question, but it kind of pokes a hole at the whole reactivity series concept and how people just don't know it too well, right? The idea about a reactivity series is if you take potassium, the most reactive metal on the face of the earth, well, in our reactivity series, and what color do I have? Let's go with green. So potassium is a very reactive metal. Note what I'm saying, a very reactive metal. So how does potassium react? What does it want to become? It turns into a potassium ion, right? Now the most reactive is potassium, and if it wants to turn into that, it becomes very stable. So the most reactive thing, when it reacts, turns into the most stable thing, and that's why it's most reactive, because the difference between stability and, so stability is the opposite of something being very reactive. The more something reactive is, it really wants to stay there, right? Think about it this way. This is how I talk to my kids about it. Like, let's say, um, you know, some some kid or some guy really badly wants a car, like really wants a car, and he has a brother who, like, it's okay if I get a car or like a phone or anything. He doesn't care too much. If both of them get it, who is more likely to keep it and less likely to lose it? Because the guy who wanted the car really bad or the phone really bad will keep care of it and always be aware where it is, and prevent it from getting damaged and everything. So that person, will be less likely to lose it as compared to a guy who doesn't care too much about it. Not that he'll be, throw his phone out the window, but you know what I mean, right? Like, yeah, he won't be as careful. So similarly, as potassium really wants to react, once it loses its electrons, it becomes in a state of mind where, like, he goes like, okay, I don't want that electron back. So it becomes really stable, right? So if you look at the reactivity series, so you have potassium, sodium, you have potassium to begin with, potassium to begin with, then you have sodium, calcium, you have, what do you have? Posoka, calcium, Posoka. But let's highlight I think you have zinc or somewhere here, and then you'll have yeah, iron, lead. That's the order of the three mentioned, and you'll have hydrogen and all the way copper. They're all trying to be ions, right? They're all trying to be ions. So over here, I won't write ions for all of them. They're all essentially turning into ions, right? Okay, let's go with 3 plus. They're all trying to be ions. So potassium becomes a very stable ion. Now this is a very stable metal. When it turns into an ion, this ion really wants to go back. So metals reactivity is decreasing as you go down. So with the arrow, as you go down, reactivity decreases of these metals. But if there was a list of ions on the right hand side, their reactivity would decrease in a more straighter fashion as you go up this list, right? So what I'm trying to say is between potassium and copper, which is more likely to turn back into a metal? Well, it's copper, right? Because copper is more reactive than potassium, because this is a stable metal. Over here, potassium, like, think about it this way, this is very stable and calm. Would it want to go into a very reactive state again, compared to something that can easily go to a less reactive state, right? Like compared to potassium, this is less reactive. Anyway, right? I hope this makes sense. So let's take a closer look. Let's look at this, what it's trying to say. Oxides become more difficult. So they say iron, lead, and zinc, but they don't mean iron, lead, and zinc. They mean oxides. So iron oxide, lead oxide, and zinc oxide, right? So essentially they're saying, in other words, they're saying Fe2 plus, Pb2 plus, and Zn2 plus. They're ions. They're in ionic form in their oxides, right? So in which direction is the difficulty decreasing? So with C, you notice that the order over here is correct compared to the reactivity series. And with D, the order is correct with the reactivity series. So with let's taking a closer look at D, zinc, iron, and lead. So you have zinc, iron, and lead. You notice how in the metals it's becoming more and more difficult for it to react, because the reactivity is decreasing. So you're going down this list, becoming harder to react. But they're not talking about the metals, they're talking about their ions, right? So it's going to get more difficult as you go up this list, right? So it's going to be, so lead, between all three of them, lead will be the easiest to discharge, then iron, then zinc. Let me just fill it out. It's slightly easier to visualize. I have lead 2 plus and zinc 2 plus, right? So zinc metal is the easiest to react and turn into an ion between the three. But zinc ion is the most difficult to turn back into a metal out of the three, right? So reactivity is decreasing. That means their difficulty is increasing as you go down, right? The difficulty is also increasing as you go up. So lead is the easiest to turn back into a metal out of the three, where zinc is the hardest. So C makes a lot of sense. So essentially, the idea is to understand that the ion's reactivity is ulta. Potassium metal is the most reactive. Potassium metal is the most reactive metal, but somewhere down here is the most reactive ion. The potassium metal or potassium ion over here is the most stable ion, you can argue, right? This is probably the most stable ion. So the most stable. Whereas somewhere down here is the most stable, right? And potassium ion is the most reactive. And somewhere here is and I keep saying I don't identify copper. Depending on what reactivity series or what question you're doing, there are still a few elements after copper, like silver and gold. So those ions would be way more reactive than if we were talking about them, right? I hope this makes sense. The noble gases argon, helium, and krypton, and xenon are present in air. Which noble gas is present in the largest proportion? And yeah, it's right. I understand why this was a challenging question. Argon is mostly would have been my choice as well. It's more of a memory thing, like you had to know. There's but because we don't even, when we're looking at the composition of air, we barely, talk about the amount of noble gases present, but we just talk about, hey, there's like a very slight portion of noble gases there. But yeah, argon is there. I think how I know argon is there is because argon's atomic mass is very close to the average atomic mass of air. Let me just take a quick look. Yeah, so argon is 18. So the average atomic mass of air is 27. So argon's 18, whereas helium is not 18, sorry. It's 40, somewhere close to 40. It's not 18, I was counting the proton mass. This is 4. Krypton is 84, about 84, and this is 132, right? And air is about 27. So which of these gases is most likely mixed with air? Like think about helium balloons. Helium, when you fill it, rises very quickly. So if there was helium in the atmosphere, all of that would rise up and separate from air because it's too light to be, mixed with air. Whereas krypton and xenon are too heavy to be mixed. The best choice is the closest air. Like that's the only way I could think of to explain it. Otherwise, you have to kind of memorize this thing, right? Because they would separate naturally because the Earth's been here for millions of years. Over millions of years, any gas that was very heavy would have separated from air, and any gas too light would also have separated from air, right? And this number we don't talk about at all, the average mass of air, but it's something good to know. And how do you calculate it? You just take nitrogen, oxygen, and other gases, and you find out their averages. And it's going to be very close to nitrogen's ratio because nitrogen is 80% of air, right? Let's move on. I think the number one distractor is, let's read the question first. There's a structure of fat over here, right? And which compound in the table have linkages that can be found in this ad? So you have ethene linkage, nylon linkage, and terylene. And the obvious distractor here is like ethene. Is this a linkage? You never argue it as a linkage, and the question is taking it as a linkage. I mean, a linkage is just a bond, right? We just call it. Yeah, so I can see why people got this wrong. Like, it's a stupid question. But yeah, you do have the ethene linkage because carbon-carbon double bond, right? You do have terylene linkage, right? Because terylene is the ester linkage. And of course, lo and behold, you have the all three ester linkages, right? Nylon linkage is going to look like this. I'm sure everyone knows. That's the amide linkage, or very similar to the amide linkage. It's gonna look like this, a nitrogen instead of the other O. And if you don't see it, it's not there, right? So it's marked like that, right? So the correct answer is C. Not a difficult question, it's just that ethene will distract people. And why would you call it ethene linkage, right? That's just silly. Okay, let's move on. Polyethene, note how they've written down, they want you to focus on the ethene part, is the addition polymer formed from monomer ethene. Which statement is correct? Polyethene can be disposed by burning. This produces carbon dioxide and water. Well, it is a hydrocarbon, so it should produce carbon and dioxide and water. And it's polyethene. Ethene is a carbon-carbon double bonded with, hydrogens on it. And if you open this molecule up, it's just going to be a really long chain, straight chain, huh? Right? So it's going to be just a act as a really long alkane of sorts, right? Sure, this is true. And what's polyethylene? It's just plastic bags, right? Your polythene bags. How do people dispose of them? By, you guessed it, they just burn it, right? Polythene decolorizes, and the reason they burn it is because over time it's so good at not naturally degrading. And by naturally degrading, what what degrades it? Well, bacteria. So that's why it's so popularly used every day. It prevents bacteria from getting into our food and stuff, but that's its ultimate flaw as well. What it's best for is its ultimate flaw, because it never gets destroyed by bacteria. It'll always be there, like thousands of years. A thrown plastic wrapper on the floor will stay there unless someone picks it up and burns it, right? That's the idea. So polyethylene is disposed by burning, because there's practically no other way. Either recycle it or burn it. Polyethylene decolorizes bromine water. Now, what decolorizes bromine water actually is the carbon-carbon double bond. Even though it says ethene in the name, there's actually no carbon-carbon double bond in it. So bromine will have no effect. So this is incorrect. This is correct. This is incorrect. Polyethylene has the empirical formula C2H4. And you'd be thinking to yourself, that's absolutely right. No matter how long I make this chain, any polyethylene will have a ratio of 2 carbons to 4 hydrogens, right? And you'd be right in thinking its formula is C2H4, but you'd be right in the, I guess, some sort of general formula. Empirical formula is the simplest ratio. So the empirical formula can only be CH2, not C2H4, because it's the simplest ratio, right? So what's the simpler ratio of C2H4? CH2. It's just you need to know what an empirical formula is. Polyethylene is acted upon by bacteria. It does not know. That's why you burn it, right? So you can burn it. So bacteria doesn't work on it. That's why you use it to wrap your sandwiches, right? So the answer over here is A. I think this question came in my mocks. Let's see. Diagram shows the fraction of crude oil. Right, you're just fractionating it. Which statement is correct? Each fraction consists of a single compound. Each fraction consists of, actually there's a range, right? There's a range. I think the first one is C1 to C4 carbon, so methane to butane. All the gases come out. Yeah, it doesn't have to be single compounds. That would be ideal though. Fraction P has the highest boiling point. Highest, I think the lowest, because it's at the top, because gases come out. Even I was pointing, I said C1 to C4, the lower carbons. Okay, the highest temperature is at the top of the column. The highest temperature is at the top of the column. No, it's at the bottom, right? Okay, oh well, because you're heating it from, okay, whatever. Naphtha fraction is used as feedstock. That's the only one that makes sense. It is there. It is that. So D, I think one of the Rutta questions are here again. Correct answer, oh my god. The correct answer is D. Substance X has a simple molecular formula, and substance Y has a giant molecular structure. Which row is correct? So, simpleton, the S looks simple as well, right? The S in simple looks simple. Okay, this is gigantic. So, water is a simple covalent molecule, and oh my god, I got electrocuted just now. And the irony is, both simple and giant molecules don't conduct electricity. Graphite does. But I got electrocuted. Giant is diamond. Well, diamond and sand, right? And even graphite. right? Let us see. What is they're asking? X could be an element only? Womp womp. Well, A and B are out. An element or a compound? That is absolutely true. It could be either or. But over here, diamond is an element, whereas graphite is an element as well. Carbon, right? So it's an element or a compound. So it's, I don't know why people find this difficult. It is D. It could be either be an element or be a compound. They're trying to confuse you. How I know? Because hydrogen chloride, if you think way, like that's a, that should be, I don't know, like ionic compound, because hydrogen is positive, chlorine is negative. But in experience, you've been told that even though it behaves semi like an ion, hydrogen chloride, like water, when we feel it's correct, we put it charges on it, like electrolysis, OH minus ions and H plus ions, the water is covalent. So these are little things show up, and I think we don't spend enough time clarifying them. And another such compound is HCl, where it's actually a gas, right? It's a completely covalent substance, but it does dissolve in water to form H plus ions and chlorine minus ions, right? So it should have a very low melting and boiling point. It's a gas at room temperature. I'm going to guess, we already have our answer. It boils before room temperature. All of these are either liquids or solids afterwards, right? So we already have our answer, and I guess that's it. But let's look at the conductivity, why not? As an aqueous solution, it turns into an acid with ions present, so definitely it will conduct. As a liquid, it does not, because it's a covalent substance. And yeah, I guess that makes it easy then. I guess the obvious issue was people thought this is an ionic substance, is how it's phrased. If people would have a much easier time if they had just said HCl instead of hydrogen chloride. It would have made it way easier. Let's move on. 18 grams of water are actually 1 mole of water, right? So 18 grams, which of these molecules have the same number of molecules over here? So 18 grams of ammonia will be 18 over 17, almost 1, but not exactly 1, approximately 1. 2 grams of hydrogen, and the MR of hydrogen is also 2, that will give you 1 mole. 14 grams of nitrogen. Nitrogen has its N2, so its MR is actually 28, so that will give you 0.5 moles of nitrogen. And 16 grams of oxygen, same story, will be 0.5 moles in actuality, because each oxygen has an MR of 32. So the correct answer is B. The diagram shows the apparatus needed to extract aluminum. We've seen this so many times. It looks complicated, but it looks like it's just is what it is. Which statement about this process is correct? Electrolyte is a solid mixture of aluminum oxide and cryolite. Well, you have to melt it, right? You have to melt it for it to, like conduct electricity. So it's not solid. So A is wrong. Let's get the pen out. This is wrong. Why would you even? The electrolyte is aluminum oxide dissolved in water. Well, if you have to heat aluminum oxide in water, I think there will be very little water. It's cryolite, right? Cryolite, I already said it. The equation for the reaction, the positive electrode is Al. I think it's absorbing electrons, right? That's going to be at the negative electrode, not the positive one. The positive carbon electrodes lose mass during the process and need regular replacement. Positive ones will, yeah, because oxygen is there, right? Absolutely. So the correct answer is D. That's the only correct statement over here. Butanoic acid is C3H7, is it? COOH. Empirical formula is, or just condensed formula is C4H8O2, which is C2H4O. Is that our answer? I guess so. Well, let's, figure out the rest. Butanol is going to be what is it going to be? C4H789 H9OH, and this is going to be, yeah, so the oxygen will prevent this. It's going to be C4H10O, right? So I can't simplify it any further. Ethanoic acid is going to be CH3COOH, which simplified is just going to be C and O and H2, right? Ethanol is going to be CH3 CH2 OH, just C2 H 3, 4, 5, 6, and O. I can't simplify it further. So yeah, A is our answer.